All right, so could you please confirm if you can see the slides on the screen? Okay, thank you. Let me approve your friends coming in. Okay, so last week we have discussed about the concept of intrinsic and extrinsic semiconductors. So we have learned that intrinsic is a pure semiconductor, and intrinsic semiconductor is a pure semiconductor where you don't have any impurities or dopants introduced into the lattice in order to alter its conductivities. And the conductivity of the intrinsic semiconductor is given by its original properties. Okay. On the other hand, if you talk about extrinsic semiconductors, they are semiconductors where you have dopants introduced into the lattice in order to alter its conductivities. And the dopants can either be from group 5 or group 3 if you assume your host semiconductor is silicon, right? So you introduce group 5 dopants into the lattice of silicon in order to make the silicon more n-type because of the introduction or the addition of electrons into the lattice. On the other hand, if you introduce dopants from group 3, you are adding more and more holes into the lattice, making the silicon more and more p-type. Okay, and we've also discussed the level of intrinsic carrier concentration for silicon. Can you still recall what is the intrinsic level of carrier concentration in silicon, Ni, the value of Ni, before we move on to extrinsic? Anyone? What is the carrier concentration in intrinsic silicon? Anyone? What's the value of Ni? Can write down in the chat box. Okay, Bala. 1 times 10 to the 10. Yes, good, Bala, thank you. 1 times 10 to the 10 per centimeter cube. So that is the value of Ni for silicon, right? So you can also use 1.5 times 10 to the 10. But if you want to ease the calculation, then you can just use 1 times 10 to the 10, which is more straightforward for calculation. You don't have to worry about the number in the front because you just have to work on the 10 to the 10 multiplying or dividing with whatever, right? So it's more straightforward. So I would advise you to use 1 times 10 to the 10 in your calculations, even though if you use 1.5, you can still, the answer is still acceptable, okay? And you won't see much change though anyway, between 1 to 1.5 if you count the calculations later on. In the extrinsic semiconductor, we have also discussed briefly about the concept of ionization, where when you introduce your dopants, either p-type or n-type, for the dopants to be electrically active, right? So the keywords here is electrically active in the lattice. So before it contributes to the improved conductivity of the silicon, you want the dopants to be electrically active, right? So for them to be electrically active, ionization has to take place, right? So for dopants, group 5, group 3, typically we need an amount of about 0.02 electron volt, as stated on this slide. We've already discussed of energy from the lattice in order for ionization to take place. Then only you're going to get electrically active dopants, which will contribute to the improved conductivity of your silicon. So let's recall what happens if you don't have your dopants ionized. If your dopants are incorporated into the lattice, but they're not electrically active or they're not ionized, what is going to happen? What do you expect to get? Anyone? We've added the dopant in but they're not active. Apa jadi? Anyone would like to answer that? Zohan? What happens, Zohan? Zohan? If the dopants are not electrically active in the lattice. Any ideas, Zohan? Anyone? Fada? Apa jadi, Fada? If the dopants are not electrically active? It will become an insulator. Yeah, that's probably one of the cases, but not insulator in this case. It's the conductivity will not improve. Okay, if you compare to the original conductivity. But what happens to the dopants in the lattice then? Any idea, Fada? Shasha? Okay, Fada said it just become undesirable. Yes, it is undesirable. But to be more specific, what happens to the dopants? Anissa, yes, defects, right? So they become defects. So they will introduce defects due to the incorporation of dopants. They're not electrically active. Okay, they will affect later on the process that we call recombination. They will induce recombination that we're going to learn later on when we talk about generation and recombination of carriers. Okay, so they will become defects, and you don't want this to happen after all. Okay, you want all the dopants incorporated into the lattice to be electrically active. Then only you can achieve improved conductivity as intended earlier on, right? You incorporate dopants to alter conductivity. Tapi kalau dopants are not active, then you don't get your objective achieved, right? So you stop in between. Okay, good. So group 3, the dopants may come from boron, aluminium, gallium. If you talk about group 5, then group 5 it will be from arsenic, antimony, phosphorus. Okay, and we've discussed about the concept of Ni, N naught, P naught, and we stopped somewhere here at around doped silicon. Okay, so let's just recap about doped silicon. So in extrinsic semiconductors, we call the dopant concentration as Nd or Na, right? Nd belongs to the dopant from group 5 because D is for donor, okay, donate electrons. So Nd donor concentration. Na belongs to acceptor concentration because it lacks one electron. Okay, so the density of both are called donor and acceptor concentrations, typically more than 10 to the 15. Okay, so when you compare your doping process, so if you talk about N-type silicon, let me just recap on this. We've discussed briefly before we stopped last time. If you talk about N-type silicon, if you talk about N-type silicon, then we're talking about incorporating dopant. Say if you're saying incorporating Nd or Na of 10, 15, for example, it can be 16, 17, it can be more than that. Okay, if you're talking at least 10, 15, then in this situation, your Nd is way larger than your Ni because your Ni is 10 to the 10. Okay, Ni is 10 to the 10. So when your Nd is way bigger than your Ni, so your N effective carrier concentration will then be approximately equal to Nd because it's like 5 orders of magnitude higher than intrinsic carrier concentration. So you can then estimate your N to be equal to Nd for N-type silicon, right? And the same goes to P-type silicon. If your Na is 10 to the 15 and 10 to the 15 is way higher than Ni, which is 10 to the 10, then you can approximate your P as equal to Na, right? So in device fabrication, the doping levels may range widely depending on the final devices, right? Some layers may need 1015, some may need up to 1019, some 17, some, well, different combinations of doping levels. So we're going to see later on when you go into the second part. So we've also discussed about this, the band diagram, how does it look like, and then the density of states, the second one, right, density of states, and then Fermi Dirac distribution function or probability of occupation, same thing, and eventually the density of free electrons or density of free holes, right, which is the product of density of states time the probability of occupation for electron in the CB and holes in the VB. So have a look at this. If you're talking about doped silicon N-type, okay, doped silicon N-type. So what happens to your band diagram? So remember last time when we talk about intrinsic, let's look at the first one, A. When we talk about intrinsic semiconductor last time, we still didn't have this state, DED, right? ED stands for donor states, right? Donor energy states, right? ED, EC and EV we've learned already. So now we learn about ED. ED means you have your donor state, and your donor state here is very close to the CB because it is N-type, okay? Because it is an N-type semiconductor where you have your electrons, more electrons incorporated, and you can then put your ED right below your EC. On the other hand, if you have your doped silicon to be P-type, where would you estimate the new energy level to be? So the new energy level in that case will be EA, E acceptor. So where would you think the EA will be in the band gap for P-type? Right, good, Bala? Near VB, right? Near VB. So it's going to be right above. It's going to be right above VB for P-type. Untuk N-type, right below, within the band gap, within the band gap. So the ED is right below EC, EA is right above VB, okay? So that's how it goes. So the same thing happens to the rest of the NE, FE, and EOPE. So if you talk about a P-type, then if you talk about N-type first, in this particular case, so your density of states will be like that. Okay, you can label it like that. On the other hand, it's going to be on the other side. And then your EF, if you're talking about P-type, N-type, sorry, your EF, this, where do you think the label will be? It's going to be up here, okay? It's going to be up there for EF N-type, okay? So we learned last time when we talk about intrinsic semiconductor, the EF will be right in the middle of your band gap, which is about 0.56 for crystalline silicon, 1.12 divided by 2, right? So right in the middle of the band gap. When you talk about your EF for N-type, the EF is going to be shifted up close to the conduction band edge, right below, okay? On the other hand, if you talk about P-type, your EF is going to be shifted down close to VB, right above the VB. So the distance between your EF to CB for N-type or EF to VB for P-type will be dependent on your doping level, okay? The higher the doping level, the closer your EF to CB or to VB, okay? You increase doping level, say, from 10, 14, 15, 16, 17, 18. So it's going to be shifted up, 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 up for N-type and down, 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 down for P-type, okay? N-type moving up, P-type moving down. So the same goes to carrier concentration. It's given by the product of NE here, density of states, and FE for NE. And then for PE is going to be given by NE, but in the valence band times 1 minus FE for P-type. So for this particular case, since we're talking about n-type, so you're going to see more electrons observed in the carrier concentration punya curve, because you are incorporating more and more electrons into the CB rather than adding on holes in the VB. So looking at this, if this diagram is given, you can tell right away that it is an n-type semiconductor because you have more electrons and holes. Okay, so what if you are asked to sketch or to draw this very same diagram, but for p-type? How would you draw that? You are asked to draw the very same diagram here, but for p-type. How does it look like then? How does it look like? If you're going for p-type, this one is for n-type. What difference does it make? Or how does it look like? Anyone? Anyone? Ada? Okay. A mirror from the original. Mirror about which axis? Fatul? It is a mirror, but mirror is about an axis, right? Which axis in this particular case? Horizontal or vertical line? Okay, x-axis, correct. So you swap the position of your here area here under the curve and this one, right? So the n is going to be a lot smaller than the p, because in that particular case, you are incorporating more of holes into the semiconductor to make it more and more and more p-type. Okay, good. So that's how it looks like. Right. The generation of free carriers requires not only that impurities are present, but impurities are either give out electrons to the CB or holes in the VB. Means they are ionized. So we have discussed this one already. So for them to be electrically active and contribute to the improved conduction, they have to be ionized, and they require 0.02 electron volt for ionization to take place, right? So this is essentially what happens. The donation of electron will be moving to the CB, and the hole will be moving to the VB from the donor states, from n-type, from the acceptor state for p-type. Okay, so this is what happens when the ionization takes place. Right, shallow impurities require little energy, close to kT, to ionize. So we've been discussing about the typical dopants from n-type and p-type. They are considered as shallow impurities, right? Our p-type, n-type dopants, the common ones, are considered shallow impurities because they only require little amount of energy in order to ionize, which is equal to kT, close to, right, 0.02, and typically they are ionized at room temperature. On the other hand, deep impurities require a lot more than kT of energy in order to ionize, so that only a fraction of the impurities present will contribute to the free carriers, because the energy is so high, and that's why the ionization fraction is only little. So only a fraction of the dopants are ionized. Okay. Deep impurities, which are more than 5 kT away from either band H, CB or VB, are unlikely to ionize. Okay. So deep impurities are defined as the impurities which have energy states. So whatever you do, you have to sketch. It's a lot easier. ECEV. So if you're talking about deep impurities, the distance between the EC to the impurity state, say EX lah, whatever, contoh EX contohnya, the energy state of that impurities, ataupun E deep, nanti confuse pula kan. Tak apalah, EX pun okay lah, EX, because deep nanti D nanti confuse dengan donor pula. Right, EX, whatever state in the band gap has to be more than 5 kT away from either band, either H, CB or VB, EC or EV, in other hand, right? On the other hand. So it has to be more than that. Then only the impurities will be considered as deep level impurities. Okay. So you can do the calculation of how much is 5 kT away. Instead, they act as recombination centers in which electrons and holes are captured and annihilate each other. Such deep impurities are called traps. Okay. When you have such impurity states in the band gap more than 5 kT away from either H, so they will likely end up as combination centers, so we call traps. So apa yang akan jadi ialah dia akan trap the electrons and holes, the active electrons and holes, and they're gonna go through annihilation process and remove from the system. Okay, they're no longer contributing to the conductivity of the semiconductor in that case. So this is where you want to avoid, or when you want to avoid, because when you do the processing later on, we're going to learn the fundamentals of the physics, but when you do the processing later on in specifically 487 fabrication, so any process that you do or you handle or whatever process that takes place will somehow have some tendency to produce defects. Okay, defects or impurities, or in fact unintended impurities from cross-contamination, for example, due to many possible root causes. Okay, katalah you mix chamber, a single chamber you mix to run certain material and some other materials in the very same chamber, but you forgot to do some cleaning before switching over to the second material, and that will introduce cross-contamination. Okay, cross-contamination can end up as defect as well, so could be categorized under this impurity case. Cross-contamination, maksudnya you don't want that material to be in the chamber or in the space or in the equipment, but they are there for unintended reason. Okay, terlupa ataupun trivial process, they're gonna be detrimental to the final devices. Okay, they're gonna kill the devices. Okay, impurities in silicon in this particular case. If you talk about other semiconductor materials, then you are talking about different impurities. So remember, in this case, we are referring a lot on silicon as the basics to learn semiconductor physics. Okay, if you're talking about cadmium telluride or zinc oxide, then the whole list of impurities will be different. Okay, some will probably be similar, cuma dia punya end state will be different, and the effect will be unique in that case, right? So impurities of silicon, if we're talking about shallow impurities, we're talking about the typical dopants, right? The p-type, aluminum, gallium, boron, n-type, antimony, phosphorus, arsenic for the typical dopants, and we categorize them as shallow impurity levels, right? So benign impurities, on the other hand, are like oxygen and carbon. Okay, benign, they could be useful as well. For example, we learned about gathering last time briefly, so they could be helpful in the gathering process in order to accumulate impurities at the passive region in the device and eventually remove from the semiconductor material. Potentially dangerous impurities like deep level impurities like La, Y, zirconium, hafnium, and the rest. Right, rare metals. Okay, they are slowly diffusing, but they are rare. We hardly use them in semiconductor processing because of their nature. Okay, satu sebab dia rare lah, they're rare, dan we don't. It's not economical to use these materials. And the most important one is because they are deep level impurity. You don't want to incorporate defects or impurities on purpose into your lattice, right? Into your silicon, because that's a no-brainer. Very dangerous for devices, deep level impurities. These are also deep level, and they are very dangerous. The first one is potentially dangerous. The below one is very dangerous, like iron, copper, nickel, chromium, manganese, gold. They're all very dangerous. So let's see why. So let's see where are the energy states of these materials in the band gap. So we are talking about so these are the band gaps. So if you're talking about the band gap, then let's have a look. You have different materials sitting here. Okay, for example, aluminum is here, gallium is here, boron is here. Those which are dangerous or detrimental to devices will normally sit close to the center of your band gap. Okay, it's close to the center, or we call them as mid-gap defect. Mid-gap defects. Your money sit in the center. That means the energy state of X, whatever, is close to the center of the band gap. They are considered as deep level impurities, deep level defects, and they are dangerous to the devices. Okay, right. We've discussed this one briefly about the EF of N-type and P-type. So remember last time when we talked about intrinsic, when you talk about intrinsic, then the EF will be right in the middle of the band gap. On the other hand, if you make it N-type, if you do more phosphorus, more antimony, more arsenate, the EF is going to move closer to, this is the original EF, if you like, EI, EFI lah. Kalau today you can write as EFI, boleh juga. EF for intrinsic, right, to denote EF for intrinsic. So as you increase your doping level, your EF is going to shift further and further up, closer to the EC, as it gets more N-type, or as it has more and more electrons available for conduction, right? So you have to learn how to sketch this, yeah, right? So remember we talked about this last time, the Fermi-Dirac distribution function. In this case, E is on the y-axis, probability is on the x-axis, and probability ranges from 0 to 1, and we discussed about 0.5. So look at this center point. So the center point is your reference, okay? So in this case, you can refer how does your center point changes from intrinsic at right in the center, sorry, to N-type, which is now closer to the EEC, okay? The center point is the main point, okay? You may mix the curve, but the center point is the main point. So if you're asked to draw E versus FE of Fermi-Dirac distribution function for N-type, Phi-type versus for intrinsic, right? So you should be able to sketch this. On the other hand, if you are incorporating more boron or aluminum or gallium to the silicon, you're introducing more and more holes into the silicon. And now let's look at the center point again. Now it changes from the center, right in the middle of your band gap, downwards, closer and closer and closer to the EV, right? To denote formation of P-type, okay? To denote formation of P-type. So is it okay so far? Up to this point? Is it all right? Can you follow? Any questions? Right, so let's move on. It looks okay. Right, the next concept that we're going to learn is law of mass action. What law of mass action? So it's going to be more and more important when you do the calculation later on. Intrinsic N-type and P-type silicon have vastly different electrical properties. Yes, of course. Intrinsic has Ni of 10 to the 10, and N-type or P-type may have different range of doping levels, but the whole idea is you're incorporating more and more electrons for N-type, more and more holes for P-type, right? For intrinsic silicon, so we've also discussed this one, N is equal to P and is equal to Ni squared. Or we discussed last time, N naught is equal to P naught and is also equal to Ni. Okay, Ni is the intrinsic carrier concentration, which depends on number of bonds being broken, which is equal to electrons a whole. You need to break a bond. Okay, you need to break a bond. Oh, and that varies, or that depends on your operating temperature. So the higher the temperature, the higher the thermal excitation, due to more bonds broken, right? So on the other hand, if we talk about N-type silicon, you can approximate your N to be equal to Nd. So as we discussed in the last few slides, because Nd is simply way bigger than Ni. For example, if you're taking 10 to the 15, which is 5 orders of magnitude higher than Ni 10 to the 10, and therefore you can estimate your N or approximate your N to be equal to Nd, right? On the other hand, in the p-type silicon, or it's missing here, you can approximate as, what is it? P is equal to, what that is the approximation here for p-type? Anyone? N-type, N equals to Nd. Yeah, okay, thanks, Father. P equals to Na, simply because if you assume 10 to 15, then 10 to 15 is 5 orders of magnitude higher than Ni, which is 10 to the 10. So therefore, you can approximate your P to be equal to Na, right? However, they all obey the law of mass action, right? Which states that the product of the free electrons and free holes, the product of free electrons and free holes is a constant at thermal equilibrium. So I'm going to use a lot of TE after this. TE means thermal equilibrium. So that means the product of N times P is a constant at thermal equilibrium. And it's not constant if it's not at thermal equilibrium. Okay, remember this is at TE. Yeah? N times P punya product is a constant, right? So let's just bring them together, bring them to an equation. What is N times P? So we have also discussed last time about density of free electrons. N equals to blah, 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 and P equals to blah, blah, blah. So we bring all both of them together, and N times P, which brings us to this equation. NC, because N is equal to NC exponential, the details, and P equals to NV, blah, blah. Remember, the density of free electrons is the product of density of states of electron in the conduction band times probability of occupation, which gives you N equals to NC, the rest. And density of free holes is given by the density of states of holes in the valence band times probability of occupation as well, which is 1 minus Fe, which gives you NV, blah, blah. So you bring them together, you're going to get this simplified equation. N times P equals to NCNV exponential of negative Eg, which is the band gap, over KT, which is also equal to Ni squared, right? So this N times P, you can then simplify it to Ni squared. Okay. Yang tengah tu dia punya content lah, the exact content if you need to plug in any parameters. But the whole idea of this is if you multiply the products of density of free electrons and free holes, you're going to get a constant of Ni squared. So we're going to use this a lot later on when you do the calculation under thermal equilibrium. Okay. Law of conservation of charge holds for both dope and intrinsic semiconductors, SC semiconductors. It states that the sum of all charges must always be 0. So in intrinsic, Pn times P, N is equal to P is equal to Ni, right? For N-type silicon, N is approximately equal to Nd, or N equals to Nd effectively. So we have learned in the law of mass action that N times P is equal to Ni squared. And this, in N-type silicon, I want it to be clear first. In N-type silicon, which carrier is the majority carriers? In N-type silicon, which carrier, electron or hole, is the majority carrier? And any of the clear? majority, then only you're going to do all the calculations correctly. Kalau ini you got it wrong, then the rest is going to be wrong as well. So in n-type silicon, yes, Bala, good. In n-type silicon, your majority carriers are electrons. Kenapa majority electrons? Majority carriers electron? Why? Why majority carriers are electrons? Bala, in your case, you can unmute yourself, you can write down as well. Kenapa majority carriers? Kenapa electrons?
We dope them with a pentavalent material, so there's an excess of electrons there, so the donors. So majority is electrons.
Yes, good. Because we want to make them n-type, so you introduce donor dopant atoms, right? Donors into the silicon, they're going to get more electrons. So kalau you go back to this page last time, if you go back to this, you can tell already, right? So we're talking about this case now, where your electrons is more than the holes, and it is n-type. So that's why your majority carriers are electrons. And then you have to get it very clear. Don't get it wrong at all, right? The majority carriers in n-type are electrons. The majority carriers in p-type are holes. Okay, now talking about n-type. The majority carriers are electrons. What are the minority carriers? Saya tanya soalan ni soalan simple je, because still a number of students got this wrong in the last batches. That's why simplicity, too simple doesn't mean it's easy, right? Kadang-kadang too simple will trick you sometimes. So what is the minority carriers in n-type silicon? Anyone? I purposely asked this simple question. What are the minority carriers? Whole, right? I want to make it explicit and obvious. Kalau majority is electron, minority will be whole. Simple kan? So kita tengok tadi, kalau you go back to the previous sketch pun, yang area of the curve besar, electron tu besar, hole kecil. So hole is the minority carrier. So now you know that in n-type, your n is equal to nd. What you don't know is the concentration of your minority carriers. What you don't know. What you know is n equal to nd, because you know the level of nd incorporated into the lattice already. So if you're talking about nd of 10 to the 16, then effectively your n will be equal to 10 to the 16, assuming you have 100% ionization of the dopants. So you incorporate 10 to the 16, all of them ionized, you're going to get n effectively equal to 10 to the 16, because all ionized anyway. Unless it is stated that only 90% ionized, then the effective concentration of the n will be n equals to 0.9 of nd. And it's going to be 9 times 10 to the 15 then, right? So kita assume all ionized dopants, so therefore n equals to nd. I don't want to make it complicated. But when it comes to the question, it may be like that. Assume 90% ionization. Then you have to do some calculation, right? Else, kalau tak disebut, and you just assume 100% ionization. So in this n-type, you know that n equals to nd. What you don't know is P, the concentration of your minority carriers. I purposely make it obvious, minority carriers. And we know that in law of mass action, n times P is equal to ni squared. Okay? So do you know the n now? Do you know the n in this equation? Yes, we know the n, and n is equal to nd, right? You don't know the P, and this is what you want to calculate. And you know the Ni already by 10 to the 10, okay? 10 to the 10 in intrinsic silicon. So then your P will be equal to Ni squared over N, or Ni squared over Nd. So this is how you calculate your minority carrier concentration in N-type or P-type silicon later on, okay? So P will be equal to Ni squared over N, and that equals to Ni squared over Nd. Then if you know your Nd, you know your Ni already, so you can then calculate your P, right? So the same goes to P-type as well. Sama je, it's just the inverse. P is equal to Na, because we assume 100% ionization unless otherwise stated. And therefore, based on law of mass action, your N is equal to Ni squared over P. Okay? Ni squared over P. And this P is equal to Na, and therefore your N is equal to Ni squared over Na. So remember, in P-type silicon, holes are the majority carriers, electrons are the minority carriers. Okay? So that's how you have to understand it first before you proceed to the calculation later on. Ada student yang still minority dengan majority pun mixed up. So law of conservation of charge states that the dope for both dope and silicon, the sum of all charges must always be 0. In this particular case, we're talking about P minus N plus ND minus NA equals to 0 because it's got to be 0 because we assume P and N are the exact values of NA and ND respectively. Okay, so that's why it's going to cancel out anyway. So keep in mind that when a donor atom gives away an electron, it has a net positive charge. Okay, so maksudnya donor atom phosphorus, for example, it gives away an electron, it's going to be a positive charge phosphorus. Okay, correspondingly, for acceptor atom, it's going to have a negative charge because it accepts electrons. So for example, boron is going to be negative charge once it accepts electrons. Right, so let's just recap the equation. That's your free electrons and free hole. Let's go for another 5 minutes perhaps. Okay, we have also discussed this one before. Density of free electrons given by density of states of electrons in the conduction band times probability of occupation, Fe, where Fe is essentially your Fermi-Dirac distribution function. Okay, and the same goes for hole as well. And P naught is given by density of product of density of states of holes in the valence band times probability of occupation, which is in the inverse, 1 minus E in this case, and this is what we got. Right, so the density of states, this is the effective density of states. Okay, so of different semiconductor materials. So let's just have a look at silicon. You can also have a look at gallium arsenide, germanium, and whatnot down here. I don't cover all those others. I'm just going to look at silicon as your reference. Once you understood silicon, you can understand the rest. Okay, so the density of states NC for silicon is given by this 2.8 times 10 to the 19 per centimeter cube for NC, right? On the other hand, for NV is given by that 1.04 times 10 to the 19. And effective mass values as well. You're gonna be using this one a lot when we do the calculations later on. Okay, I think I'm just gonna let me cover a bit on degenerate. So the next concept that you will learn is called degenerate semiconductor. So let's just go for another few minutes. So a degenerate semiconductor is a semiconductor with such a high doping level. So remember when I talk about extrinsic, so within extrinsic, you're gonna get this degenerate semiconductor under certain condition. So dia bukan intrinsic because it is a dope semiconductor. We're talking about dope. So but remember last time we talked about when you dope your semiconductor, it may range from say 1014 up to a very high level 1019 to be considered as extrinsic semiconductors. But within this extrinsic, there's a range where the semiconductor will turn into a degenerate semiconductor, still within extrinsic semiconductor domain. So the value of doping must be very high to be eligible to be called as degenerate semiconductor. In this particular condition, the material, if you're talking about silicon, is going to start to behave more like a metal than a semiconductor. So it is still a semiconductor material, but then the way it behaves electrically is more of a metal than a typical semiconductor, simply because the doping level is way higher than the typical range of doping level in semiconductor. So it occurs when the doping concentration more becomes equal or larger than the corresponding effective density of states. So you're going to get degenerate semiconductor when your doping level or doping concentration, same thing, has a level of equal or larger than the corresponding effective density of states. How do you get this value? Or where do you get this value? Effective corresponding effective density of states. How do you know what is the value for this? Kat mana nak cari? You just have to go back to the previous page. Okay, effective density of states is already given for a specific semiconductor material. So in this case, silicon is NC equals to 2.8 times 10 to the 19, NV 1.04 times 10 to the 19. So the moment you have a doping level hit this, or more than, equal to or more than this, then your material is considered as a degenerate semiconductor already, equals to or larger than the corresponding NC or NV. Okay, so you are going to compare with NC if you're talking about N-type silicon, because it's C, conduction band, remember? And you are going to compare doping level with NV when you are comparing your P-type. Okay, some other, if you talk about N-type, whether it's degenerate or not, then you have to compare with this NC. If you're talking about P-type silicon, degenerate or not, you have to compare with NV. Then only you know whether it is already a degenerate semiconductor or not. So at which point in particular we're going to have this degeneracy. Okay, degeneracy is dia punya the mechanism, the process or the event where you have a degenerate semiconductor. So you are going to start to have degeneracy when your EF, still you have to sketch. Okay, go back to your sketch diagram. Then we can appreciate the magnitude. Okay, when EF is less than 3 kT from band H, less than 3 kT, maknanya dia terlalu dekat, right? So that means if your EF here, if you're talking about N-type, your EF should be here. Let me just put it EFN, sebab N-type, to distinguish from this below P-type. Kalau you put EF alone pun is understood already as long as you know it's N-type or P-type. Okay, so, tapi for this particular case, I'll just distinguish in order for you to understand. EF for N, EFN, EF for P, EFP. You can stick to this notation if you like throughout your answers or whatever, because I understand it already, right? If you have your EFN, the distance of separation to EC is less than 3 kT. You can calculate 3 kT. So then you already have degeneracy. Okay, ataupun you already have your degenerate semiconductors. Okay, on the other hand, if you're talking about P-type, with respect to EV, your EFP here is already 3 kT or less. Maknanya 3 kT atau lebih lower than 3 kT away from EV, then you already have your degenerate semiconductors at hand, right? So apa jadi if you increase further doping? You increase the doping further. Kalau dah sampai you have already exceeded or equal to NC, or already equal or exceeded NV, but you keep increasing. So that means you're talking about you have hit 10 to the 2.8 times 10 to the 19 for N-type, but you keep increasing. You want to go for 5 E19, 7 E19, 9 E19. What happens? Okay. Apa jadi ialah EF will go above EC or below EV. It can even go into the EC or into the EV when you exceeded this. Okay. So let me just finish off with this slide, okay? In 1-2 minutes. So in this particular condition, your EF, so now note where is your EC and EV. So where's your EF now? It's already into the conduction band for N-type. N-type. It's already into your valence band for P-type. Okay. this is what happens when you keep increasing your doping level above 2.8 times 10 to the 19 for n-type, or 1.04 times to the 19 for p-type. You keep increasing the doping level. What happens to the energy state is actually going above EC or below EV, right? So I'm saying into EC or into EV, same thing. Okay, so you can also represent this as the below one, n-type degenerate semiconductor, when your n0 is more than your nc, more than or equal to, if you like, which is comparable to 2.8 times 10 to the 19 for this, and 1.04 times 10 to the 19. Right, and then if it goes into your EC, then your EF will be more than EC. EF more than EC for n-type. If you keep increasing, if you keep going up, and is going to be EV more than EF. It's now EV is higher than EF for your p-type. Okay, so this is what happens when you talk about degeneracy. So next, in our tomorrow's class, we're going to continue this. So we'll be going to look at what are the examples of materials which fall under degenerate semiconductors. What are the examples of material? Even though you can actually dope silicon to beyond NC and NV, but there are also some other materials that are quite common or popular in terms of the applications for semiconductor devices. All right, so I'm just going to stop here. Any questions so far on dope semiconductors, p-type, n-type, intrinsic, a bit of degeneracy introduction? Is it okay so far? Do you have any questions at this point? Can everyone follow the course so far? All okay? Is it difficult so far? Ada apa-apa yang you lost before and you couldn't follow at this point, and you lost and you don't know how to continue anything? Yeah, yes, of course you have to. Well, remember is one thing, but you have to understand first, right? Remember is okay, but you have to understand the concept. If you understand the concept, like the typical notation EC, EV, EF, intrinsic, extrinsic, the concepts, then the remembering will become easier. But I don't encourage you to remember over understand, right? Understand first. The remember is only a complementary to that, but understand first. Okay. Yeah, I don't deny that there are quite a number of parameters to digest, and equations as well. Okay, so I think you can hopefully can manage that. Right, so any other questions? Any previous concepts that you don't understand at all? Oh, exactly, public holiday. Thanks, Bala. Thanks, Bala. As a loophole when it comes to public holiday. I marked already on the calendar, but when it was in the class and I just forgot. Yeah, tomorrow's public holiday, there's no class. Okay, so we'll move on. We'll continue with our Wednesday's morning class, 9 a.m. Okay, with degenerate semiconductors. Thanks Bala. Kalau tidak nanti saya masuk Webex, so saya sorang-sorang aja. Yang lain semua tak masuk Webex. Right, thanks a lot. So the rest okay? Previous concept okay? You can follow so far. I want you to understand that you can follow the course so far. Yeah. Being online is very difficult if you don't understand and you don't ask. If we were in the class physically, then I can tell at least from your faces. You there's certain things that you want to ask. Tapi being online, if you don't understand and you don't ask, I don't know. There's no way for me to tell. Right? And you don't ask offline WhatsApp couple, you don't ask, then I'll just assume that you know. Okay. So if you don't know, please ask. You can ask in the class or you can ask offline. It's okay for me. It's right for me. As long as you can follow the course well. Okay. So if there's no question, I'll just assume that everything is okay. It's going to be more and more difficult after this, especially when it comes to calculation. You have to, imagine a lot and do a lot of sketches before you can do the calculation. My advice is, when you want to do any calculation, even though it is the simplest calculation in this particular course, sketch first. EC, EV, EF, EI, whatever, EFN, EFP, sketch first. Walaupun you rasa in your brain, this one is easy, I don't have to sketch, I can do right away, I can tell already. Sketch first. Give meaning to the values before you can process well, right? Physics is about giving meaning to the numbers. Kalau you tak sketch, then if you get the answers right, but you don't sketch or you cannot articulate well, then it's not physics, right? Try to give meaning to the numbers, then you punya mind processing will be a lot clearer after that, right? Okay, I'll see you Monday. Sorry, I'll see you Wednesday morning then, right? Bye-bye, take care, Assalamualaikum.
Thank you, Doctor.
No worries, bye.